Hello student, welcome to the Wave Optics course. Today we have lecture number 43 and today we are going to start a new topic which is called the Fresnel diffraction. So we have today lecture number 43. I am going to start today a new topic as I mentioned, which is Fresnel diffraction. So before that, let me quickly remind that diffraction, the phenomena diffraction was broadly divided by two parts, two types. One is Fraunhofer type Fraunhofer diffraction and another is Fresnel diffraction. So in Fraunhofer type diffraction, you may remember that the source and the screen both are at infinity. The structure was something like this. So essentially we deal with, so this is the source where the light is emitting, and then we place a lens here so that we can have parallel ray that makes the incident light, the source, to be infinity. Then we have some aperture here, and then again we place a lens here, and in the screen, so suppose light is diffracted and then we accumulate all the light here at some point P and we find a pattern here, but essentially source and screen both are at infinity. This is source and that is screen. Fresnel diffraction on the other hand is the structure is rather simple, that if I have a source here, it is emitting light and it is interacting with this aperture, and then we will get some pattern here out of that. In this case, what happened, that light that is falling to the aperture will be spherical wave, and then that is coming here and reaching here is also a spherical wave, and since both are infinite, the setup is simple and we will going to get a pattern here. On the other hand, in Fraunhofer case, the light that is coming here, that is hitting to this aperture, is not a spherical wave, rather it is a plane wave, and whatever I get is captured here in this screen. In this case, this is source and it is screen. Different cases are discussed in Fraunhofer under Fraunhofer diffraction problem. For example, we discuss the single slit, problem, we discuss double slit problem, we extend this idea to discuss multi-slit problem, then we discuss also what happened for circular aperture and rectangular aperture. So, these 5 problem we discuss in detail with all the calculations for Fraunhofer diffraction cases. Now, we are going to do a similar thing in Fresnel's diffraction cases, but you will going to see that the treatment will be completely different here, and the basic reason behind that is the light that is coming here is no longer considered to be a plane wave, rather it will be considered to a spherical wavefront that is coming, and based on that we will going to do all the treatment. So, before going to do a problem here in Fresnel diffraction case, we try to develop that what is the theory and what is the background mechanism to get a intensity at this point P. So, let us start with that. So, in Fresnel's case what we do is this. So, we will start today with the basic understanding of Fresnel's diffraction. So, Fresnel diffraction. So, as I mentioned here, the source and the screen are in finite distance. They are in finite distance. So, let me draw here that if this is the source and what happened from this source, spherical wavefront we are going to emerge, and let me draw a portion of this spherical wavefront. It will emerge like this. I am just drawing a portion of this wavefront which is no longer plane but spherical in nature. And then we have an aperture here through which the light will fall. So, let me draw that first. So, this is the window. And here we have a window like this. This is O. So, this is a point, say this is small cross sectional area, and the light that is coming to this point is say r prime, and this is my S, and the light that is coming through this window is some point here, that is P, and this is R. This cross section is dA, the cross sectional area. This is the point O, and this is the structure we have in our hand. Okay. So, the electric field at point O in the aperture at this point here, the electric field. So let me write this point. So, this O, that is the origin, and this is another point, say O prime. So, the electric field at O prime, that is the area having the small area dA, that patch in the aperture is E naught is equal to E s divided by r prime e to the power of I k r prime minus omega t. So, note that this is a spherical wavefront, that is why 1 by r prime term is there, which was not before in the case of Fraunhofer diffraction problems. Now, this quantity E s divided by r prime e to the power I k r prime are considered to be a complex amplitude. That we know, that E I can write it as minus omega t, and this E0 tilde is basically the complex amplitude. This is complex amplitude. Now, the contribution to the resultant field at point P due to all small area. So, due to the small area, what is the contribution? If I try to find out that contribution here, I can write that is the, so the contribution to the resultant field at P, that is I am talking about this point now, at P due to the small area dA, that is I am just try to find out the contribution at this point P due to the small area dA, that should be DEP is equal to D E naught divided by R e to the power of I K R minus omega t. Since P is in the finite distance, so the wave that is coming from this dA area will also be a spherical wave, and if it is a spherical wave, then that should be the form 1 by R e to the power I K R minus omega t, that is the form of the spherical wave, and D E naught is a small amount of magnitude that is there. So, the amplitude here, note that, so the amplitude which is D E naught divided by R, which is the amplitude that is proportional to the area dA. That is, if dA is large, then the contribution of the electric field will be large at the point P. So, I can write it as D E0 by R is essentially, I just write EA by R dA in this way, where EA is the field amplitude per unit area. If dA is the field amplitude per unit area, then dA multiplied by area is the field amplitude. So, this is the field amplitude divided by R. In the left hand side also I have amplitude divided by R. So, dimensionally it is fine. So, now EA again proportional to the complex amplitude of the original electric field that is falling here. So, if I go back and see that DE0 is somehow related to, so the amount of field that is coming here is somehow related to the field that is coming from S. So, we can have that EA should be proportional to A, and if that is the case, I can write that EA is proportional to the complex amplitude that we had earlier, and that is E naught tilde. And what was E naught tilde? Where, let me write down, E naught tilde was ES divided by R prime e to the power of I K R prime, that we already had. So, EA is essentially a constant alpha. This is proportional size and this is a constant alpha, and that will be multiplied by this. This is a proportionality constant here. So, ES by R prime e to the power of I K R prime, that we have. So, if EA is known, then from this expression that dep is E0 by r. So that I can write. So okay, so let me see what notation we use here, and here we use the small area, and yeah, here E0 by A I write EA, and EA is this quantity. So essentially we can have this. So DEP which was equal to E0 divided by R. E0 divided by R is EAR dA, and EA is this. So I can write directly alpha, then ES divided by R prime, then I have e to the power of I k r prime multiplied by e to the power of I k r minus omega t. I just put the value, and that value, if I simplify, because one is e to the power I k r prime and another is e to the power I k r, so I can write it as alpha Es r prime e to the power of I, then I have k r plus r prime minus omega t, and then I should have a dA here, So I correlate the source is, and then I have an aperture here with small area and a point here P, and the light is going like this. So I correlate the electric field here to whatever I have here, which is EP, and it related to this area dA. So now I want to find out what should be the total field here. Then what we supposed to do is we just need to integrate over this aperture, and that we do. So the total field at P that is EP, and essentially that should be the integration over dA. So it is equal to alpha Es, then we have e to the power of minus I omega t term that should come outside because that is nothing to do with the integral over area. Then we integrate over the entire aperture, and we have 1 divided by r prime e to the power of I k r plus r prime over dA. So that is the total expression we have, and that expression suggests that how the total field at P is related to the field at S, and if I know everything, then by doing this integration I can find out the field that is there at P. So, that is the structure. But in this calculation few things are neglected. Let me in the book you will find these factors, and that thing we are going to neglect here. So, EP, let me draw once again, let me write down once again that EP is equal to alpha ES, then e to the power of minus I omega t, and then over the aperture we have 1 divided by r prime e to the power of I k r plus r prime dl. That is the overall integral, but few things as I mentioned is neglected. First thing is this expression does not take account the obliquity factor. Normally this obliquity factor we write as f theta, and expression wise f theta is half of 1 plus cos of theta. So, what is obliquity factor? That if I have a source here, if I want to find out something here, then theta is 0. So, from this I can get the f theta value is 1. But if I move to other point, say here, so this is my P, and if I move to another point P1, then I am with this horizontal line I am making an angle theta, and as soon as I am making angle theta, the factor, so that we will going to reduce, the amplitude will going to reduce here because of this obliquity factor, and if I move more and more wide angles, then this value will going to change. So, that value is essentially called obliquity factor, and we neglect here in this calculation. We consider that if you go back to the figure, we consider that for whatever the ray I draw is nothing to do with the angle theta, but which is not essentially the case, but we neglect here for simplicity. Also another thing is neglected here in this expression when we calculate the total field by taking account the integral over this aperture. So, does not take, so pi by 2, there is a pi by 2 phase shift of the diffracted wave related to the primary diffracted waves relative to the primary incident wave, and that pi by 2 factor is not, we did not take account this. So, we will going to discuss this in the coming few classes, that how these things are there. So, let me first run. So, does not take into account pi by 2 phase shift of the refracted wave relative to the primary incident wave. We are going to discuss this in the coming few classes. So, that condition is also not taken into account in this treatment. So, that is the overall thing. So, today I do not have much time to go forward with this idea, but the point is today I try to develop from the very straightforward expression, which is the circular which is the spherical wave that is emerging from a source, and if it is hitting some aperture, then it get diffracted by this aperture, and we are going to get some pattern at the screen. So, if this pattern is emerged there, then what should be the electric field that we calculate with this expression that is shown here. So, in the future classes we are going to exploit this expression and try to find out what is the total field by doing certain integration, etc. But there are other simple method that we need to learn before, and in the next class we are going to do exactly the same thing, and we will start something called, we will learn something called Fresnel's zone construction, that how by not doing that rigorous calculation, by simply using the concept of zone, we try to find out the intensity, or at least get the idea of the intensity at some point due to some aperture. Okay, so with that note I would like to conclude here in today's class. Thank you very much for your attention, and see you in the next class.